Hello, everyone. This is Chen. Today, we will cover two topics in assignment 2 for COMP5425. And the first one is about the JPEG encoder in image compression. And the latter one is about the motion estimation in video compression. So let's look at the first one. The first part is that implement a JPEG encoder from scratch. This tutorial will show you how to implement a sample JPEG encoder step by step. So here's a pipeline of the JPEG encoder. Giving an input RGB image, we firstly to convert it into YCBCR channels. This is because we humans are sensitive to luminance, but less sensitive to chrominance. So we can do subsampling for chrominance to further reduce the storage. Then we split the image into several 8x8 blocks. And for each block, we apply a density transform. And after the transform, we do the quantization for the coefficiency. And then we will apply the DPCM and the ILC and the Huffman entropy encoding to obtain the encoded image. Finally, we will write the encoded image into a JPEG file. So this is the whole pipeline of the JPEG encoder. In this tutorial, what should you do? You are required to implement the following parts. The first one is about color transform. That is, we convert the image from RGB to YCBCR format. So I put the formula here. And the next step is to do sampling image blocks. And you are required to implement this method for YUV 444, and YUV 422, and YUV 420. You may be get a puzzle about the YUV 422 and YUV 420. Here I put a figure to illustrate the format. So for YUV 444 format, if we sample 4 pixels for Y channel, we should also sample 4 corresponding pixels for UV channels. In other words, there is no subsampling for luminance and chrominance. So the resolution of YUV 444 should keep same as its original resolution. As for YUV 422, we can say that the resolution, the horizontal resolution become half of its original, and the vertical resolution keeps same. That means we should sample 2 pixels horizontally into a new pixel for UV channels, but keep the Y channel at the same as its original resolution. And for YUV 420, we can say that the resolution become half of its original from horizontal and vertical directions. So that means we should sample a region 2x2 into a new pixel for UV channels. Also, we should keep the Y channel as its original resolution. So that is the YUV 420 format. And here, I will show you how to correctly sample these blocks. So for the sequential mode of the JPEG encoder, for example, for the YUV 444, for each YUV channel, we split the image into 8x8 blocks. That is the micro block, such as B1, B00, B01, B02, B03. That is from the left to the right, from the top to down. And about for YUV422, because we sample pixels from the horizontal direction, so the microblock become 16 by 8. So that means this is a microblock, and this B02, B03 will be a microblock, and B04, B05 will be a microblock. So for a microblock 16 by 8, for the white channel, we still use 8 by 8 blocks. That is, we have two blocks for the white channel. But for U and V channels, given the 16 by 8 microblock, we should subsample it into a new 8 by 8 block. For example, B00 and B01 will be subsampled into a new block. And we need to sample the B02 and B03 into a new block. Sample the B04, B05 into a new block. Similarly, for YUV420, the size of the microblock becomes 16 by 16. So for white channel, we have 4 blocks for the white channel, and then we sample this 16 by 16 block into an 8 by 8 block. Oh, so there exists an error, and that is the order should be changed between the YUV422 and the YUV420. Okay. After sampling these blocks, we need to do the density transform. Here, I put the formula of the density transform. So the time complexity of the original density transform is big O of n power 4. And there are many optimized solutions that can be found online. Once we implement the above functions, we can test the JPEG encoder with the provided image data at G0 PNG or other images you can test. You are encouraged to test images with different quality and YUV format settings. So in this tutorial, what will you achieve? You will learn the pipeline and details of a JPEG encoder, and you are encouraged to implement a sample in JPEG encoder for fun. For example, giving a PNG image with size over 30 million bytes with your JPEG encoder that can be compressed to JPEG file no more than 1 million bytes. If you use the source code from the GitHub, remember clone this report with a recursive way, because we use the submodule Google test and the PUI band 11. So for CPP users, we use CMake to build this project. Actually, you can use other compilers like Visual Studio. If you want to test the class image or other functions, you need to open this flag that the build test is on. And if you want to build the Python interface, you should enable this flag. Here's a usage example of the JPEG encoder. We input an image, and this is the output image. We assign the quality to 30, and we expand the format to YUV420. And here I list some APIs for image class. This is about load an image from file. And this is about the copy of images. And this is about assign the pixel value to 10 at the location y, x, z. Now we can copy an image from different types. So the task for CPP users, you are required to complete functions in the source JPEG encoder.cpp. Okay. So for Python users, there are two methods to install the JPEG PY. The first one is to use the CMake. The second one is directly use the setup.py. I also list some API for your reference, such as the YUV format and the JPEG IO and Huffman codec. So for Python users, the task is that you are required to complete functions in Python JPEG encoder.py. Okay, I will show you how to build this project. First, you need to clone this with a recursive way. Okay, let's make a directory build. We can enable the flag build tests. So this is a test for the class image. Oh, there's an error. Oh, because we do not have the data, we should go to the above level. Okay, we can say that the 4 tests have been successfully passed. And we can use the JPEG encoder to compress an image. We need to give the, let's say, here, if we fit incorrect arguments, it will throw an error like this. So we need to input image data. And we are specify the output data. With the quality and the YUV format. because we do not have implement the RGB to YUV444, so it through an exception. We can say that. So this is the main function and the source encode.cpp. And this is the API of the JPEG encoder. So here, encode RGB. So the first step is to convert the RGB to YUV format. You should implement this function here. And then we will do the sampling image blocks. You should implement the sample to blocks. And then blocks for FDCT. We can say that it was not implemented. So you should implement here and delete this line. After applying DCT for each blocks, the several parts, including the quantization and data tag ordering and entropy encoding, have been provided. Then the program will write the encoded data into a JPEG file. So I will show you a successful case. Okay, we have built the executable file, and we have the data here. We can say that before compression, the image file will cost 34 million bytes. Here we use this as the input, and we want to compress the image with quality 30 and with the format 420. Quality F. So the original image had the shape of 4,000 by 6,000. And after compression, we obtain the encoded JPEG. Let's say. Oh, this is the original image. And this is the JPEG file. Impressive. We can see the details about these two images. Let me put them side by side. Okay, you can see here on the left is the original image, and the red one is the JPEG image. You can hardly to distinguish these two images. Um, you can see the details. The artifacts are more obvious than the original one. But the overall quality is good. Okay, so for Python users, you need to implement functions at the JPEG at the Python JPEG encoder.py. Let me show you the details. First, you should build the JPEG py fill the Python setup install or use the CMake, and you need to modify the environment JPEG py path to your actual directory. Then we can import APIs like read RGB image, YUV format, JPEG IO, and Huffman codec. Here we read RGB image here. We specify the color format to YUV444, and the quality is 50. And the output JPEG file. And the first step is to do the color transform. That is, we should implement the RGB to YUV. Then we divide the image into blocks and do the sampling. Notice that if the image cannot divide it totally by the block size, we may need to hide the image with zeros. Then we need to implement the DCT transform here. Actually, this function here is the FDCT transform is similar to CV2 DCT, but you are not allowed to directly use the CV2 DCT or other external libraries. And here we define the standard quantization tables with quality 50 for luminance and for chrominance. And this function get quantity table will linearly scale the quantization table with the specified quality. And we will do the quantization for the DCT coefficiency. After the quantization, we will use the zigzag scan to reorder the coefficients. Then we will do the DPCM and the RLC coding. And this is achieved by the Huffman codec. So we directly put the coefficiency after zigzag ordering to the Huffman codec. And we will obtain the encoded image here. Finally, we will write the encoded image into a JPEG file. So this is the whole pipeline of the Python version. Okay, I'm enjoying it. Thanks.